Excuse me. Morning, everyone. Okay, so, uh, and I apologize in advance, but I agreed to do a presentation at Tempe High School at 9:30. They want me there at 9, but I told them I don't finish till 8:50. So, but I won't have office hours today. Uh, what I am doing with office hours is I've requested this room. I found we don't have another class till 10:30. So what I'll start doing is keeping office hours right after class. So if you have a few questions, you can stay a few minutes or an hour and a half, but I'll just do them right here in this room, and it gives us 15 probably more minutes that we can all interact as need be. And the room's sort of filling up. I've been having 3 to 4 students. If I start having 5 to 6, my room's a little tight. So we could have 100 students come and we'd be fine here. So I want to make sure that the office hours are open to everybody. We're in 15.3, so we're getting close to the end. Monday we'll do 15.4. That's the end of chapter 15. We do have an appendix lesson, so we'll do that. So we've got 2 more, Monday and Wednesday, and then we can start preparing for the test. So that kind of gives us 3 days for review and going back over what we've learned. So I want to point out what's always been here is there's an exam one review resources. That is, right now, it's just a PDF form that's prepared by the course coordinators who also make the exam. So they give you some questions to practice on. So that's a good form. What I'll start doing is I'll go through and I'll start making some solution videos of those questions so that if you work through them and get stuck, you can watch them. It'll kind of be a little bit of review over the concepts, but we'll do that when we do our review. I've got a question bank. I'll get up more questions that are like this. We'll work them here in class, kind of do a mock test where we can work together, but just to make sure. So if you come, you'll be there. I'll post all those resources in Canvas as well. So if you don't make it to class, you could still have those resources and work through them. But again, coming here is good because then you can talk it out, and that oftentimes is where the learning occurs. It's not just doing it silently, but working with someone else, or if you do get it right, explaining it to someone else will solidify it in your mind. So we're getting close to that, but we're not there yet. We still have maximum and minimum to do. So again, this is taking us back to what we did in Math 210 with calculus. However, remember, we're in 3 dimensions now. So we're using X and Y. It's not like the implicit where it's on still 2 dimensions. We're really using X, Y, and Z. Okay, and so we'll get through this. Now, we didn't finish up with the second derivative, which was sort of part of 15.2. But what I'm going to do is I'm integrating it here because at the end of this presentation, we're going to use the second derivative. So I'll do that example right before we use it. Why not know why we're going to use it right away? So it's incorporated in here. You'll be able to go back to 15.2 and do those 2 problems. And then you'll also be able to use that here. All right. Any questions or comments? All right. So we're going to talk about maximums and minimums. So the high points and the low points. Now, when we're talking maximum and minimum in this case, we're talking about what makes the largest z value or smallest z value. Okay. So, and it takes X and Y working together to make that happen. So we're going to see, we also get a new type of extrema today as well. So here it is. We've got a 3-dimensional figure, right, in X and Y. It's like a little mound. And it can be formed by this equation, 1 minus x squared minus y squared. So it kind of looks like, I guess, in a 2-dimensional world, an upside down parabola, but it's a 3-dimensional version of it. So you could actually cut this out, probably use it. Parabolas are great. 3-dimensional parabolas are great. Those are what our satellite dishes do, because anything that would bounce in here, the way it's shaped, it all goes to some sort of focus point, and that's how satellite dishes work. Although we don't use them as much because we have streaming now. So, but it was a great technology in its day, and it still uses. Uh, Notice it's over the surface. This point A is a maximum Z value, which means it is a higher value than any other Z value, at least in this area. And if this is all that we have, it's also an absolute maximum rather than just a relative. Now, this could come back here and go up, and this could be a relative depending upon where we're going. But for this particular picture, this is it. So this is all we're considering. It's the absolute because it's the highest of the high. Okay. We'll look at some other examples. We'll use one of the things we're going to do is we're going to teach you how to find maximums visually like this. So we're looking at graphs. So we're going to use the 3D version of Desmos. The thing is that's not going to be available to us on the exam. So as we move to the exam, we'll probably focus a little bit more on one of the techniques in the end of analytically finding these things. But first of all, it's kind of learn how to do it. So this has graphed that formula, that function with x squared plus y squared, and it gives something like this. I'm going to get a better view. I did it on Desmos, saved it. So if you pull up these slide links, you can actually click on that. That will take you into my Desmos, and you'll actually be able to pull this up and work with it. So let's do that. This picture wasn't really doing it for me, so I made my own picture of it and found a few little extra tools in here. If you go to the tools, you can make the shape translucent, which is going to be helpful because then we can kind of see through it, and you see that there's kind of this minimum. And then also once it starts spinning, you can kind of just let it spin. But you can see you've got some four maximum points, and then it dips down here. This looks like a minimum point, maybe a relative minimum, because you have this external side that just keeps going down, right? And again, we can use this and kind of move it around. Oh yeah, there's the 4 points up there. If I go to, yeah, that does look like a minimum point. You can kind of turn it around. So you can use Desmos to answer, at least verify some of the maximum and minimums that we're going to do. Because we'll show you how to find these points analytically with taking derivatives, but we'll also want to identify them. And while we're here, I can't remember the complete order of how I was doing this, but where is it? Okay, so we can say, yeah, these points here, 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 and here, those would all be maximums. And they would be absolute rather than just relative because they are the tallest. There's nothing any taller than that. Okay, so those will be absolute maximums. Does that all make sense? Now thinking about our calculus, what happens at a maximum to the derivative? When you're up here, your derivative is a tangent line, right? What kind of a tangent line is this going to be? What kind of line is this? Horizontal, right? What kind of slope does a horizontal line have? 0. So that's what we're going to use that technique, is that we've got partial derivatives, right? X and y. They will both be 0 when we have a maximum or a minimum, right? That's the thing, is it's 0. We don't know whether it's a max or a min unless we take a look at it. So we're going to do that. But there's that one, and then do it this one down here. That's a minimum, and we could call that a relative minimum because we know it's not absolute if we're going to consider this whole thing, because this comes down here lower, but it's in that area. It's the bottom of the valley, right? So it's a minimum, relative minimum. And again, the tangent lines, the derivatives are going to be 0 there because they'll be horizontal. Tangent lines will be horizontal. There's one new type of extrema that we get. It's what happens. See, I don't know if this is, but it's what's happening right here. We can see in the y direction, right? y comes down, so there's sort of a y minimum there, right? Y is at a minimum here. But if we think in the x direction, what's happening, the x comes up and over, and I got a better picture of this. So for x, it's a maximum, but both derivatives are going to be horizontal tangent lines, right? Because minimum, maximum. But it's, so we could also get these type of points. New one for us. Looks like a saddle, doesn't it? So we call it a saddle point. I guess if you're into horses and stuff, you might recognize that as a saddle point. So now we've got three things that happen when we've got when the partial derivatives x and y are both zero. Then we have either a maximum, a minimum, and again they could be either absolute or relative, and we could also have a saddle point. And the thing is at the end we're going to use a second derivative test, just like we did in the other calc, to figure out whether it's a maximum, minimum, or saddle point. So there's kind of a little test we use for that. But the first derivative, all we get is zero. We know it's one of these three. And that's pretty much what we're talking about. Any questions on that? Awesome. And I got, again, a couple better pictures that we'll go through. Um, here's one that shows the saddle point a little bit better. So they zoomed up on it. It's a maximum or it's a minimum in the y direction, but a maximum in the x. So we get this little sort of saddle thing happening. It could be a very important thing because it does tell us how the rates of change are interacting, and sometimes that's a good place to be. But saddle points, okay. And again, you have access to these. These are my particular ones. If you go, I've also given you access to the textbook's full version, which is a lot more words and writing. So if you kind of want to read through that, that may be helpful. I find it sometimes more confusing. In fact, I took out a lot of their stuff because this could apply to 3, 4, 5, 6 variables as well. But since we're going to focus just on 2 variables, let's just focus on that, right? We'll get that down and then we can apply that later if we need to. That's how I think of things, rather than getting all this notation. So how do we locate these extremas? Well, we just did it one way by looking at it. And in the homework, they will give you sort of that. If they give you, so there's a little practice, and it's pretty evident. They'll label the points, and you just have to say, is that a minimum, a maximum, or a saddle point? So you'll visually do that with a few of the simpler ones. You won't actually have to come up with it. But we want to also be able to get the location. So to do that, we've got 3 steps. We'll take the partial derivatives, f of x and f of y. Notice I use my notation, not really mine, but it's the one I like, rather than that fractional notation. But you could use either one. We set them both equal to 0 at the same time. So we'll get a value for x and a value for y, and sometimes multiple values for x and multiple values for y. And we'll do some examples which give us some x and y points. Those points are critical points. I don't know, let's label them that, call them critical points. That's what a critical point is. It's where the first partial derivatives are equal to 0. And we got a max, a min, or a saddle point. Okay. Oh, here it is. Yeah, they're called critical points. I knew it was in there somewhere. And the cool part is, we don't do proofs in this class. You know, in the math, if you're a math major, you might have to prove this, but it's a fact that if they're equal to 0, this is the only place we're going to get critical points. It's the only place we're going to get minimum, maximums, or saddle points. This has to happen, and if this happens, that's what we get. Okay. So let's look at one example. We're talking about the domain as a whole Cartesian coordinate plane, so it's everything. We're not limiting the domain. The partial derivatives are defined at every point, which means it's a nice smooth curve. Again, these are all things we need, but we'll give you those. And we want to find the critical points. So how do we find the critical points? Step 1, Thank you. Partial derivatives, x and y. So we're going to do that. Step 2, set those derivatives equal to 0 and solve. Yes, step 3. So partial derivative of x. Oops. Let's go back. I'll do it here. So the partial derivative of x. So x cubed, when I take that, it's going, the 3 comes down, subtract 1 from the exponent, and that's the derivative of x, right? When I come to the derivative of y, we got to be a little careful here. Remember, because this is something squared. Even though when I take the derivative of y, I'm going to get 0, I'm now taking the derivative of the outside, which is just some function squared. So I'm going to get plus something squared. The 2 comes down. And I subtract 1 from the exponent. So that's to the first power. Now I use the chain rule. I go inside and I take the derivative of y. What's the derivative of y when I'm doing the partial of x? 0. So this is one of those mathematical things, if you forgot about doing this and you just called it 0 at the beginning, you would have been okay, right? Because now we're going to, whatever that is, we're multiplying by 0. Whenever we multiply by 0, what happens? It becomes 0. So what we got is that our first derivative is just equal to 3x squared. Again, you may remember this, but I want you to think through that there is a derivative that we get this, but it disappears because when we take the inside derivative, all we got is 0. Now there's a possibility there could have been an x in there, something, I don't know. But anyway, all we got is 0. So far, so good? Okay. So then let's take, and then we'll do the next step, but let's go ahead and take the derivative of y. So take the derivative of y, x to the third is going to be what? 0, because it's a constant, right? It's just a number. We're holding it constant. So we get a 0. I'm going to go ahead and put that in there. And then now we take this derivative of y minus 1 squared. And again, we remember the chain rule. The 2 comes down, y minus 1 to the first power. Take the derivative of the inside. Derivative of y now, since y is a variable, is 1, because it's 1y, right? And derivative of negative 1 or minus 1 is 0, so it's 1 minus 0, so that's just 1. So finally, we see that the partial derivative is just going to be 2y minus 1. Okay? We now set these equal to 0. Could divide both sides by 3, so we get x squared. 0 divided by 3 is still 0. Square root of both sides. Square root of 0 is still 0. So x equals 0 is one of the answers. That's the x answer. That's all we got. I guess you could say it's plus or minus 0, but 0, that's still 0. Over here, we take this one, set it equal to 0. And notice by doing this, this makes a lot of the arithmetic easier. Divide by 2, oh, that's still 0. Add 1 to both sides, y is 1. So we get a point and let's see if we did all three. Check that the points are in the interior of the domain. Okay, they told us the domain is everything, so yes, they are in the domain. Okay, if they limit the domain, it's possible we could get some points out here that we're basically not even talking about, but this is where we're at. Okay, set them equal to 0 and solve for x and y. We did that. Okay, so we got our 2 points, or a point. Now to figure out, this could be a maximum, could be a minimum, could be a saddle point. Actually, if I'm remembering correctly, what I need to do one thing we can do, right? Because when we're talking about a maximum minimum, we're talking about what kind of a value, x, y, or z. We're talking about a z value. So we need to find out what that value is, and that might be helpful. So to find a z value, what we do is we start with the original function. We're going to plug in 0, 1 into this function. Because really, in 3 dimensions, this is not a point yet. It's just an x and y coordinate. So we know where x and y is, but we don't know where z is yet till we plug it into here. So I might be getting ahead of myself, but let's go ahead and do this. When x is 0, we get 0 cubed. Y is 1, so we get 1 minus 1 squared. It looks like we get 0 plus 0 is 0. That's the z value, right? So our point really is 0, 1, 0. We're going to graph this, and we're going to see when x is 0, see how does this work? Yeah, x is 0, y is 1, so y will move over, and z is 0. So we should see a minimum at that place. So again, oh, we got another one. That's why. I was thinking I did this example. So anyway, we went through that example. You could graph it, and you would see that that's where you would get either a minimum or a maximum. But that's just how to do it. So we're going to take this one. It's a little more complicated, a little more interesting. We're going to actually get a couple more critical points, and then we're going to go to the graph and identify if they're minimums, maximums, or saddle points. Okay, so let's take our original function, classifying the critical points. First thing we need to do is get those critical points, right? So we need the derivative with respect to x, the partial derivative with respect to x. Let's do that. So up here, I've got an x squared. I take its partial derivative. The 2 comes down. I have my x, and I subtract 1 from the exponent, so it's now x to the first power, right? Y is a constant, so it, as I say, just sort of tags along for the ride. It's not 0 yet because we didn't take its derivative. It's just like the 2 stuck up. Well, that 2's there. It's a coefficient. It's a number. Does that make sense? Derivative of minus x squared is going to be minus 2x to the first power, right? We're taking derivatives here. And then the last one is 2y squared. When I take that derivative with x, right, that's going to be 0. I'll put that in there. So we got a minus 0. Okay. Going to take the partial derivative with respect to y. So I've got x squared y. I take the derivative of y. It's 1 at this time because y is our variable now. X is a constant. So the x squared, so it's 1 times x squared. The x squared is still left there because I'm not taking the derivative of it. I'm just taking the derivative of y. Does that make sense? Just like if I had 2y, I take its derivative. The derivative is 2. X squared y, derivative is x squared. Okay. Derivative of x squared now, this one in the middle, it has no y, it has no protection, has no bodyguard. It's 0, right? Because it's just a number. X squared is just a number here. So I'm going to put minus 0. So that middle term, when I take the derivative with respect to y, it's gone. It's 0. The last one, minus 2y squared, right? The 2 comes down, so we're going to get minus 2 times 2 is 4. Subtract 1 from the exponent, we get y to the first. So this is our y partial derivative. Okay. We're going to take each of these, set them equal to 0, and figure out what we get. So when we set x, this partial with x, we get 2x minus y minus, oops, wait, no. 2xy minus 2x equals 0. And notice yeah, that's what we got. Want to solve this for x? Yeah, let me, we can factor out the x. That's probably, at some point, we're going to have to do that. So factor out an x. What's that? Oh, you can take the 2x, sure, sure. Might as well take it all. So you take the 2x out, and that would leave y minus 1. Does that make sense? So a little bit of algebra. We could do this. And now I've got two things, right? I've got 2x and y minus 1 being multiplied. When two things multiply and give you 0, what do you know? One of them has to be 0. The only way you get 0 from multiplying things is one has to be 0. So then either 2x equals 0 or y minus 1 equals 0. So this one we solve, well, 2x equals 0, that means that divide both by 2, x equals 0. That's one of the values. For y, we add 1 to both sides, y equals 1. Okay, so those are values. Again, we'll plug it back in the original, and we'll see what kind of points we get. Good so far? Good. Maybe not, but let's see how we go. So for this one, oops, no, we're going to set this one equal to 0 as well. We've got x squared minus 4y equals 0. So then we get x squared, add 4y to both sides, x squared is equal to 4y. That didn't give us a value, did it? And we can't. We've got two variables in here. But what we do have is we've got x equals 0 and y equals 1. We can plug these into here and see what happens. Okay, because we do have some values. It just tells us that x squared equals y is a, I don't, probably a, well, it's x squared. It's probably a curve. It's some sort of a curve on this that it's following, but only some of these points will be critical points. So I could plug in x equals 0. So that gives me 0 equals 4y. In this case, what is y equal to? Y has to be equal to 0. Divide both sides by 4. So that gives us, again, look at, we got two values for y now. We could plug in 1 for y. So that gives us over here, x squared equals 4 times 1. Well, that means x squared equals 4, which means x equals what? Take the square root of both sides. X equals 2 and negative 2. We don't want to forget about the negative 2, because right when you square something, you square negative 2, you get positive 4. You square, so that's, I always forgot about that second one. But so that's going to be 2 or x equals negative 2. Okay, so this gives us a lot of candidates. We have x could be 0. Sorry, x could be 0, 2, or negative 2. Y we came up with is 1 or 0. So we got all these different values for x, y, and z. And so we have to try them all out. And we see we get multiple points. We see we get a 0, 0. We get a 1, 0, 0, a 0, 1 possibility. We get a 2, 1 and a 2, 0 as a possibility. We get a negative 2, 1 and a negative 2, 0, all as possibilities. So there's 6 points, kind of 6 critical points we have to check. All these combinations of x values and y values. Now, one way is we could plug them in. Let's see. I think there's some, these negative 2 zeros. think we're okay. So we have done that part to classify these. Good, we're good on time. We're almost there. And basically, I'm going to stick with this. Whoa, it's a weird looking. And that's why the 3 dimensions, a lot of times you have to move it around to see what's going on. So do you see there at 0, 0? That's like a relative maximum, right? It's a little bubble towards the top. If we come this way, what does it look like here? So that looks like 1, 2, 0, go straight down, right? What does this point over here look like? Stop. If it was on a horse, you could call it a saddle, right? It looks like a saddle point on either side of that maximum. And then we had, what did we have? We had these other points here. So that explains 2, 0 and negative 2, 0, 0, 0. How about 0, 1? Let's see. Oops. Come back here. 0. Let me see. Where's my y? There's my y direction. Looks like 0, 1 would be like right here. What does that look like? Zero, x is 0, y is 1. Z is going to go down there. It doesn't look like, I mean, it's just a surface that keeps going down. So sometimes we get these critical points, but they don't do it for us. Okay. So far we can identify. Let's change colors. That 0, 0, we call that a relative max. 2, 0, right? Oops, I'm upside down now. So x is 2, y is 0. I didn't go off and I go straight down. I get saddle points on either side. So these are both. And then if I look at x is 2, y is 1. So x is 2, y is 1. That's going to be along this surface. And that also is not a min or a max. Remember from 210, sometimes that would be like an inflection point. So we're not going to get into inflection points in 3 dimensions. That kind of, but those could end up being some sort of an inflection point. So sometimes we get these zeros and we have to look at the graph and say, no, there's no max or min there or saddle point. So we leave those alone. Does that make sense? But notice how we really have to, independently, we can't do too much, except we're going to get one more test. Yes. It's in the yeah, they cancel them out because they didn't end up being a max or min. But in the initial, you use it as a thing to examine. Yes. But they're not points we have to worry about because they didn't give us a max, a min, or I don't know. We'll figure that out. Actually, I'm going to give you a technique. We're going to use a second derivative. But I've got to look at what the exam is and what they're providing. But yeah, we can't use Desmos. We also can't use Microsoft Excel, which we're also going to use as a method here. Okay, let's see. So another way, and I set this up with Microsoft Excel. So in the homework, they're going to give you some tables like this. So they'll produce these for you. Okay. There's our x and y's are up on top. These are the z values. And so taking the first derivative, we've got it down to 3 points now, right? We have it down to, so let's take a look. 0, 0, 0, 0 is right here. What is happening to 0, 0 if I go in the y direction up or down? 0 becomes negative 2y. I'm going down, right? So I've got lower values, which means 0 is bigger than that. So I've got a max in the y direction. What's happening in the, sorry, a max in the, yeah, max in the y direction. How about in the x direction? 0 goes down to negative 1 on both sides. So in the x direction, I have a max. So I have a max in the x and the y. This is a maximum. So here's a way to kind of analyze it. Now, you could do this with your calculation, but I would never expect this on the exam. So we'll worry about the exam and how we're going to do it. I got to see what kind of questions we're going to ask as well. But yes, we're limited as far as what we can do on an exam because of this. So let's look at the other question, the other ones. 2, 0. So here's x is 2, y is 0. Let me go back to that. Keep these. Let me just make sure I called that right. Oh, see? You got to look in 3 dimensions. Those points are not 2, 0. They're 2, 1. Right? This is 0, 0. This point is 2 in the x direction, but it's 1 in the y direction. See, that's how working with 3 dimensions. And the thing is, we're going to find it here. So I got to undo these. My saddle points are actually here. Not here. Okay. And the rate I'm telling that, oops, go back here, is when I went to 2, 0, 2, 0, look what's happening. Well, negative 4 is bigger than negative 4 is bigger than negative 10, but it's smaller than negative 2. So I'm getting something that's not, it's not a maximum in that y direction or a minimum. And the same thing happens, negative 9 is less than negative 4, but negative 1 is bigger. So I just, it's on the surface. I can kind of see this here, right? So it's kind of like I need the graph, but the graphing tools are not perfect. At least I didn't look at the right view, right? But I came over here and when I did this one, I said, wait, 2, 0 is not a saddle point. But 2, 1, watch what happens when I go to 2, 1. And I'll change colors here. When I go to 2, 1, let's go to red. Then when I go, look, I got these matching points, negative 4, negative 4. Negative 2 is bigger than negative 4. But when I go this route, I get negative 2 and negative 2. I get a constant. I'm wondering if there's a, I'd have to check that. So I've got a maximum in the y direction, but sort of a constant in the x. That would give us a saddle point as well. I'm suspect about this line now because, again, I created it. What you can do is if you go back to the original PowerPoint, it's got the textbooks one. They highlighted some stuff, so I wanted to take those off. This doesn't look right to me, but see if x is 1, or say y is 1, and then you got x squared. Oh, yeah, you get x squared minus x squared. You got 1, you got 2. X squared minus x squared is 0, so you're always going to get negative 2. That kind of just didn't look right, but it is. Yeah, let y equal 1. Then you get x squared minus x squared, which is 0. 1 times negative 2 is always negative 2. Okay. And then the other point we looked at was negative 2, 1. Which is here. And again, the same thing's happening. Negative 2 is bigger. So it's negative 2 is bigger than negative 4. So it's a sort of a maximum in the y direction. But in the x direction, it's sort of a constant. So it's not a maximum. It's a saddle point. Okay. So that's just a technique you're going to be, I think 2, maybe 3 questions. They give you a table. You identify the critical points, and then you use that technique. Yes, sir. Yes, you'll always see that the two don't give you the same. So one will be a minimum, one will be a maximum, or a maximum and a constant in this case. We go there. We still didn't get into second derivatives, but we got a little bit of time. So let's also analyze this with second partial derivatives. Okay, so I'm going to come back here. What are our partial derivatives? This was the partial derivative of x, right? 2xy minus 2x. And this was the partial derivative of y. So we're going to need to start with those. Actually, I'm going to, instead of doing separate ones, let's just take the ones we've done. That's about all we're going to have time. Over the weekend, I'll do a video of some other examples, but 2xy minus 2x. And then f of y was, thank you, x squared minus 4y, right? I think I got those right. Yeah. Okay. So what we're going to do is we're going to focus on the partial derivative of x. We're going to take second derivatives. Now, second derivatives, we can take a derivative of a partial with respect to x or a partial with respect to y. Okay. So we actually get 2 second derivatives. So we'll label this one as the partial derivative of x with respect to x. So the second derivative we're taking with respect to x. So we come up to this here, and this first one, 2xy, its partial is going to be just 2y, correct? Right, the derivative of x is 1. And then when we get to minus 2x, its derivative is 2. So this is the second partial derivative of x with respect to x. Okay. Also, we could have taken this partial with x with respect to y. So notice there's 2 partials. So we're using the partial with respect to x. This first part, 2xy, we take the derivative of y, that's 1, so we have 2x. And then we take the derivative of negative 2x, since we're taking the derivative of y, that's 0. Okay, so this second derivative is just 2x. Be okay with that parts, okay? So it's just the starting place is we start with the partial, and then we take those 2. We do the same thing with y. So let's take the partial of y with respect to y. So it's really a true second derivative, right? X squared, that derivative with respect to y is 0 because it's a constant. And then the derivative of minus 4y is now just going to be minus 4. So far, so good? Yes, sir. Because we're taking the derivative of y. So when you take this part, that's just 2x, but this part, there is no y. This is just a constant. It's 0. So really, yeah, it should be 2x plus 0. think of it. That's so good question. So then when we take, watch what's going to happen here. If I do this right, we should end up with the same thing. We're taking this derivative of partial derivative of y. We're taking the second with respect to x. So now this one with respect to x is going to be 2x, right? Because the x comes down and we subtract 1 because we're taking it with respect to x as a second derivative. Derivative of 4y is 0 because that's got the, notice these ones are the same and they will always be the same. So that's a cool part. You really only have to do one or the other, and then you know the other one's going to be exactly the same. If you want for a while, you can take them both, but it's a good way to check. They will always be the same. Okay. So in our limited time, I'm going, and again, we'll maybe start off Monday with some questions. We have time. I'm okay if we take all next week to get all the new material. We still have 2 full days for review plus a weekend, so we'll be doing well. I'm going to skip over these. I will do these as a video post later on, just so you can see. And again, you just take the first derivative and then you take these 2 second derivatives. But what I want to show you is how what we use it for. So in this part, I will probably also do a follow-up video where I actually work through the problem. It's going to take a little bit, but we do this sort of formula. So we take the derivative of x with respect to x, so that partial, times the derivative of y with respect to y, that second partial derivative. We multiply those two and then subtract the partial of x with respect to y. Remember, this is the part that's always the same, squared, so that's why you can square it. You could multiply them. But for some reason, that ends up being called a Hessian. Probably some guy named Hessian came up with this idea, so he put his name on it. That's what they always do in math. But the thing is this gives us, if this equals, well, depending upon what it's equal, it tells us whether we have maximums or minimums. So first of all, if the Hessian is positive, we don't care what value. It could be 10 or 15 or a million. But if it's positive, then we look at the partial with respect to x, the second derivative here. If that is greater than 0, we've got a minimum. If the partial with respect to x, the double one, is less than 0, then we've got a maximum. Okay, so so this formula, as long as it's positive, it gives us just that result. We'll either have minimum or maximum, and all we have to look at is the second derivative of x, f of x. Okay. If h is negative, then there's only one other thing that could happen, and that would be that we have a saddle point. So the negative means we've got different things going. One's a max and one's a min, so that's a saddle point. And finally, if it's not positive or negative, it has to be 0, because that's the only number that's neither positive or negative. Then it doesn't tell us anything. It's inconclusive. Sometimes that happens in math. We have a test, oh, it doesn't tell us anything, right? And then we got to go to the graph, and hopefully the graph will help us. But when we're in 3 dimensions, as I demonstrated well today, it's difficult to read those 3-dimensional graphs. You got to really be careful. And even when you're careful, it's hard to really see what's going on in 3-dimensional space. But we'll work with you, and we'll figure out ways that it works on the test. Partly I need to see how they're testing. They might not ask these types of questions. They might ask something else where it's more conceptual, and I would hope for that, because we can't get too technical. So this is part what we're going to need, and we'll see. Like I said, I got to see what they're providing and what we'll do. But that's the use of the second derivative. Here's an example I would go through, which is what we were working on. And since we're getting really close to the end of the class, I'll do this on video. We've already done the seconds. All we got to do now is plug it into that formula, and we're good to go. Okay. And again, we'll work through stuff, get your questions. Monday we'll pick up from here and make sure it's all good.